All right, so in this first section, we're going to talk about what is infinity. You've probably heard the term infinity thrown around in many different contexts, both in and out of math. Maybe you've heard that a real number can be described as having infinitely many decimal places, or maybe you've talked about the behavior of a function as it goes to infinity. Infinity is not a number in the traditional sense. Instead, it represents the idea of something that is unbounded or limitless. Sometimes, especially in the discrete math context, we use the word infinite to describe the size or the cardinality of a set, or maybe a particular kind of an order in an infinite or boundless set. In this context, even though infinity is not a real number, you might be able to talk about different sizes of infinities or even do operations on those objects like addition or multiplication. And if you have taken classes with me in the past, you might have talked about this, and you might know about me that discrete math is the area of math that I particularly enjoy. Now, in analysis, we use infinity instead to describe behaviors and patterns, like sequences growing without bound or processes that continue indefinitely. We might even talk about values that are arbitrarily large to suggest infinity without assigning it a value. Even though we can't ever reach infinity in this analysis sense, we can still use it in rigorous ways to make sense of real-world phenomena. It might help to think of infinity as a direction rather than a destination. And so why do we care about limits, right? About what's happening sort of as we approach infinity. So limits allow us to make precise statements about processes that approach a particular value but might not necessarily ever reach it. Now we saw some examples of that in the warm-up, right? We saw the concept of limit coming up in the context of compound interest, right? As we compound more and more frequently, the balance approached a limited value rather than growing in an unbounded way. We also saw limits come up in the context of probability, right? As we added more and more balls to the box, we found that the probability of winning our game approached 50% for each player without quite reaching it. And we also saw it in the context of infinite sums. Right? We saw that in order to describe operations on infinite decimals, like 0.3 repeating plus 0.6 repeating, we might need an infinite series to make that operation explicit. And so these are all examples where, right, infinity is not really existing as a real number, but we kind of need that concept of infinity to describe what's happening to something in a concrete way. And so all of these really point to the need for a precise concept and a precise definition of a limit. That's something that we're going to be working towards in this class. Once we do that, we'll be able to use the concept of infinity, or use the concept of a limit as something approaches infinity, in order to describe or predict long-term behavior. Let's see, move this down a little. Right? We're going to be able to predict long-term behavior. We're going to be able to model change in the real world. And we're going to be able to assign values to processes that seem to be incomplete or seem to be infinite. So assigning values to seemingly incomplete processes or infinite processes. So limits provide the foundation for understanding calculus, particularly in defining the derivatives and integrals. So for instance, if we wanted to look at the limit as n goes to infinity of 1 plus 1 over n raised to the n, this is equal to the real number that we describe as e, right? That we use the symbol e to describe. This expression defines a constant which arises naturally in growth and decay process. Actually, we saw this come up in the warm-up problem with compound interest. In fact, limits are critical for describing any kind of exponential function on the domain of real numbers, which we'll also see here, right? So we can see that even though this is something that is defined in calculus and that's necessary for calculus, we use these ideas of limits in very concrete ways, even for secondary math. So let's look at an example of that. So if we're thinking about exponentiation, right, when we first introduced exponents in middle school, maybe even earlier, typically where we say the base is a, we usually initially introduce it where the exponent b is some positive integer. Like if we wanted to describe a to the third power, our base is a, our exponent is 3, and we define it to just be a times a times a, right? And this is a really concrete way to describe what exponentiation means when you're introducing it to students for the first time. Later, we can use that definition and use some of our intuitive ideas of how this works to define a to the b for a negative exponent, right? Like we learned that, say, a to the third power over a to the fifth power means a times a times a over a times a times a times a times a. And then we can use what we know about division to get that this ends up being 1 over a squared, right? But we also learn our exponent rules, which tell us we can subtract our exponents here, and we get a to the third over a to the fifth is a to the 3 minus 5, or a to the negative 2, right? And so we use this sort of basic definition of exponentiations as a positive integer in order to define a to the b for negative values, right? So we have that a to the negative 2 just means 1 over a squared. And then similarly, we can expand to define exponents that are rational numbers, right, that are fractions, right? We know that a to the 1/2 power really just means the square root of a. And then we can start putting those together to say things like, if I wanted to compute a to the negative 2/3 power, well, we can rewrite that as 1 over a to the 2/3 power, and then we could rewrite that as 1 over the cubed root of a squared. Okay, and now we've sort of rewritten this as in a very concrete way that students at least have a sense of what it means. But what about for an irrational number? Right, so we have this we have an idea of how to compute these things and what they mean for integers, for positive integers, negative integers, for rational numbers or fractions. But what about when your exponent is an irrational number, like a to the square root of 2? Well, for students who've never seen that before, they might not really know what that means, and sure, they could plug it into a calculator if a had an actual value, but what does it mean to raise something to the square root of 2 power? In order to do this, we really need to understand that any real number r, including the irrational ones, has an associated infinite sequence of rational numbers, we'll call it r sub n, which converge to r, which get arbitrarily close to that real number r. So for example, if we wanted to compute a to the square root of 2 power, and we want to know what that means or how we would compute that, then what we need to know is that the square root of 2 is an irrational number. It's going to have an infinite decimal that doesn't repeat, right, or it doesn't terminate. So it starts like this, 4, 1, I think I have that wrong. I think it's 4, 1, 4, 2, 1, and so on. But we can approximate that real number with a sequence of rational numbers, right? A sequence of numbers, like we can say, let's let r sub 1 just be 1.4. And that's a rational number because it's got a terminating decimal, but you could also just describe it as like 14 over 10. Okay, and then r sub 2 is 1.41. Okay, so we could describe that as a fraction as 141 over 100. And so on, R3 is 1.414. Okay, that's 1414 over 1,000, and so on. Whoops, running out of space here. But if we have this infinite sequence of rational numbers, then each one of these has a sort of more concrete understanding, right, of, let's call this a sub 1, which is just going to be a to the r 1 power. So a to the power of 14 over 10. Right, we know what that is. That's the 10th root of a to the 14th power. Similarly, a2 would be a to the power of r2, and that's going to be a to the 141 over 100 exponent. So the 100th root of a to the 141th power, and so on. And so when we try to figure out what is a to the power of the square root of 2, what we're really doing is we're going to look at the limit as n goes to infinity of a to the rn power. That's going to approach some fixed amount, and that's what a to the square root of 2 really means. So it allows us to meaningfully define irrational exponents using limits, and that's going to ensure consistency and continuity in the exponential function, right? If we wanted to define the function, a to the x power, where a is some real number, having this limit definition and really making that explicit is going to allow us to show that that's actually a continuous function. Note, that's not the only way to define a to the b, where b is an irrational number, but it is a useful way to see why we might need to make limits, or why we might need limits to meaningfully define an operation that's common in, say, pre-calculus. All right, so using infinity in real-world problems. We often encounter situations that are modeled by infinite processes, like, for instance, repeated compounding in interest in finance. So we already sort of saw this earlier, but compounding interest. Processes that have diminishing returns or decay. Right, there's lots of examples in physics or biology or chemistry that have to do with processes that involve diminishing returns or decay. And probability distributions, right? Normally in secondary math, you're looking at sort of discrete probability, but if you're looking at probability distributions with infinite trials, you need limits that require that, so, involving infinite trials. So understanding limits can help us to model and predict the behavior in these systems. Now, our textbook describes a number of teaching principles, and one that's of particular interest here is to acknowledge and revisit assumptions and mathematical constraints and limitations. It's often necessary to describe mathematical ideas to students without providing the rigorous definitions behind them, right? You're probably not going to get into the epsilon delta definition of limits when you're teaching calculus for the first time in high school. But that's just because students don't yet have that mathematical maturity to understand them. As teachers, our job is to understand the careful definitions enough so that we can communicate the bigger picture in an accurate but also an understandable way for students. And that's really the goal of this class.